Hello everyone, I'm Tamás Lovas, and this is the module Capturing Reality and the submodule of airborne mapping. So we will talk about airborne mapping, airborne photogrammetry, drone photogrammetry. So we're going through the aerial mapping technologies, airborne photogrammetry, airborne laser scanning, and drone photogrammetry. So photogrammetry, as I gave you a definition in case of remote sensing, this is the same ISPS definition. Photogrammetry is the science and technology of extracting reliable three-dimensional geometric and thematic information, often over time, of objects and scenes from image and range data. So this is kind of a wide definition, but it contains that we can collect, we can acquire geometric and attribute data in the same time, often over time, so we can analyze time series. And if we want to distinguish between the data acquisition technologies, these technologies can be spaceborne, airborne, or UAV or drone, or obviously we can capture images from the ground, so there are terrestrial photogrammetry applications. These are the UAV and terrestrial photogrammetry are considered the close range technologies. It's very interesting that the UAV photogrammetry, so when we are collecting images from a drone, the geometry of them, so the geometric positions and orientations of the images are more similar to terrestrial laser scanning that compared to that of the airborne terrestrial photogrammetry compared to that of airborne photogrammetry. Okay, in aerial mapping, I show you on the top image, you will show a typical location scene of airborne photographs. On the image below, you can see if we are collecting images that have overlap between them, and by the way, there is overlap between the imaging rows, then we can evaluate the 3D of each of the points from the overlapping areas. Just think of, you see your finger from the left eye and from the right eye, and your brain combines them in 3D. And if you can see both images that have an overlapping area, and one image is projected to your one eye and other to the other eye in appropriate equipment, you can see it in 3D. Now, this is done by automatic algorithms, and so this is evaluated automatically, and the result is a point cloud. Previously, like 20 years ago, 25 years ago, we still use analog cameras. Nowadays, we are using digital cameras. Okay. In case of laser scanning, we are not on the platform, on the aircraft, or on the drone. We put laser scanners instead of cameras. The navigation should be resolved by GNSS that provides the location data, the position, and INS, inertial navigation system, that is using, for example, inertial measurement units. That is the rotation along three coordinate axes and accelerations in three directions, and that can be used also providing location data between the GPS signals, the GNSS signals, and providing orientation data, so it shows where the sensor sees. So obviously we have the sensor, in this case it is a laser scanning, and the platform, a fixed wing, it can be a fixed wing aircraft, a helicopter, or a UAV, which can also be a fixed wing UAV or a multi-rotor UAV. Obviously there is a main difference, for example, in the payload. In case of a fixed wing aircraft, we can carry more load, and we can travel farther because not the rotors give the uplift force. And in case of a multi-rotor drone, we can use a gimbal and put different sensors on them. And the multi-rotor drones are better to land and take off. They are better to follow the horizontal and vertical directions, the topography, but they don't fly too much because it depends on the battery time. Okay, in aerial mapping, the end product is often a point cloud. This is an image what the students are doing. For example, they are classifying the point cloud. In the middle, you can see they can classify roof top points, vegetation points, and ground points. We can also derive orthophotos. Orthophotos are the images without vertical and horizontal distortions, so you can measure distances them like on a map. So this is, for example, an orthophoto from the Parliament of Hungary. That's interesting that the laser signals are not on a spot on the ground, but they have a rather big footprint, like 30 to 40 centimeters in practice. And these laser cone hitting the ground can be reflected from the top of a tree, from the middle branches of a tree, from the vegetation on the ground, and from the ground. So we can make difference between several returns, several pulses. So that means we can, from just to distinguish between first and last pulse, we can remove most of the vegetation. So that means laser can penetrate through the vegetation. As opposed to photogrammetry, when we need two images to capture the 3D coordinate for the points, in case of laser scanning, from one emission we have 3D. And if it can penetrate through the vegetation, we can have the ground points, even in forest. So you can see on the left side, or in the middle in this case, that's an area with the vegetation, on the right side without vegetation. That's the same, that's from Karlsruhe. Now you can see the buildings and the vegetation. If I just considering the last pulse, then the vegetation is removed without any kind of filtering. So that's a main difference between photogrammetry and laser scanning, that it penetrates through the vegetation and we can capture points from the ground and we can remove the vegetation easily. In case of drone photogrammetry, that's a bit different, because drones are flying with lower altitude, and you can operate them. You can fly over different objects. On the right side, you can see when we are flying in a grid. So in a grid, in a raster, we just code them with the operating software of the drone and the object, and it can compute how many images do we need about that. But if you want to capture the facade of a building, or fly around a tower, or go inside a yard, then you need to use free flight. And at the end, if you can check the normals of the captured images, you see that we are collecting hundreds or thousands of images for capturing. This is, for example, the main building of BME, but the result is a 3D point cloud. This is a 3D point cloud of our campus in Budapest. So if you are evaluating the aerial mapping, the advantage is the scalable resolution. So you can scale what kind of sensors you use, what altitude you use, what flying speed you use. You can scale the resolution. You can reach a homogeneous coverage, like as it was in the remote sensing. It's an efficient technology for large areas. In case of UAV, drone photogrammetry, this is an affordable technology. So you can buy drones in the some thousands of euros. It provides a flexible image capturing geometry. So you can have oblique images, nadir images, and it's very easy to use, easy to learn how to capture these images. But what about the shortcomings, the disadvantages? It's obviously weather dependency. If there is strong wind or rain, that you cannot fly your drones. The shadows and uncovers can still occur. So if there is in certain times of a sunny day in the shadowed area, it's hard to recognize any kind of objects. The price can be disadvantages, especially for traditional aircrafts. It's the flying hours are very expensive, the equipment is very expensive, and human resources is very expensive, because there are a limited number of experts able to fly and capture photogrammetric images. And in case of drone imagery, it can be applied only for limited areas. It depends on the battery life, so you need to be prepared that for limited areas you can use this technology. So I collected again some references, books, and web links, so feel free to look them up, and thank you for your attention. In the next video, we will check the terrestrial laser scanning technologies and use cases. See you next time. Goodbye.